We will now look at example 24 to further reinforce our concept of how to find the nth root of a complex number. Now in this case, I want to solve this complex equation which says that z to the power of 5 is given by this complex number over here. And what this tells me that is that z should be just equals to this complex number to the power of 1/5. Right, which means I want to find the fifth roots of this complex number here. And what I notice is this question has specified that I want to find this in exponential form, which means that I'm going to begin by expressing my complex number in exponential form. So if I were to find the modulus of 16 minus 16 root 3i, then I will get the square root of 16 square plus 16 times of root 3 whole thing square. And this I can evaluate to be a value of 32. On the other hand, I can find the argument of this complex number to be equals to tangent inverse of 16 over 16 root 3, which I can find to be negative pi over 3 radians. And therefore, expressed in exponential form, my complex number is as such. Now the next step is to keep adding 2k pi to the argument to obtain it in n-1, and in this case n equals to 5 different ways. So what I can do is I'm going to change only the argument. N is going to be negative pi over 3 plus 2k pi. And as we saw in example 23, I could allow k to take on the value 0, 1, 2, 3, 4, and 5, or I could also use this set of values of k, negative 2, negative 1, 0, 1, and 2. Okay, and in this case, for this example, I'm going to choose to illustrate using this set of values of k. So the next thing I'm going to do is to state the nth roots by taking the nth root of each one using De Moivre's theorem. Okay, so 32, I need to take it to the power of 1/5, and I find that this is equal to 2. On the other hand, for the argument, what I need to do is to divide this by 5, and thus I get this new angle over here, while my values of k are as such. So therefore, substituting these values in, I would find that in polar form, my roots will actually be as follows. We will now look at example 25, which is the last example on this concept of finding nth roots of a complex number. It has been wrongly printed as example 14 in your notes, so please change the numbering. Example 25 actually consists of two different parts. In the first part, I want to find the 6 roots of 8i in the form re to the power of I theta, where r and theta meet the usual conditions for modulus and argument. Okay, so without further ado, I will leave you to work this out, because I know that I want to leave my roots in exponential form. Therefore, in step 1, I am going to convert to exponential form. And by now, this should be something that is quick and easy for you to perform. Then in step 2, I am going to create my n-1 equivalent values by adding 2k pi, and k is going to take on the values of 0, plus minus 1, plus minus 2, and negative 3. Now subsequently, I find that I can easily proceed to step 3, which is to find the n different roots. And this is done using De Moivre's theorem, so I can obtain the new modulus of each root by taking by taking the 6th root of 8, and I can obtain the new argument by dividing the original argument simply by 6. And therefore I have arrived at this point. So what I want to do next is to write down the 6 different values of z, which I will get by substituting in these 6 different values of k. Okay, so for example, firstly I can substitute k equals to 0. So pi over 12 plus 0 times of pi over 3 will just be pi over 12. Similarly, I can substitute in k equals to negative 1. and that will give me pi over 12 minus pi over 3, which gives me simply a value of ei to the power of negative pi over 4. In a similar fashion, we can work out the 4 other roots, and I will list them down over here without going through the exact working for you to check your answer. So please work through this on your own and ensure that you are able to obtain all these various roots. Now that we have completed part 1, we are ready to look at part 2, which tells me that given that I over w to the power of 6 is equal to 8i, I want to deduce the 6 possible values of w. And just by comparing part 2 and part 1, I notice that the complex number in both cases is the same. So what this means is in part 1, I have found values of z such that z to the power of 6 equals to 8i. And therefore, comparing these two, I know that I therefore want to find w such that 1 over w is actually equal to z, which is the same as saying that w is 1 over z. Then what can I say about the modulus of w, and what can I say about the argument of w in relation to z? Well, from what I have learnt in the earlier part, the modulus of w will be just 1 over the modulus of z. And this is basically 1 over root 2, which is found from part 1. Similarly, the argument of w can be found to be the negative of the argument of z. Depending on which root of z we are looking at, it is going to vary. Okay, but all I know is that it's going to be a negative. So for instance, looking at this first possible value of z, the corresponding value of w will actually be root 1 over root 2 e to the power of I negative pi over 12. And thus, by doing this substitution of all the modulus to be 1 over root 2 and all of the arguments to be the negative of the original angle, I am able to deduce the 6 possible values of w just by using the result in part 1. So the key learning point or the key technique to take away here is to compare the equations in part 1 and part 2 to observe a reasonable substitution. With that, we have come to the end of this section on De Moivre's theorem. In the next section, we will be looking at some of the geometrical effects of arithmetic operations on complex numbers.